Chung-Yun received his bachelor's degree in physics and maths from National Tsing Hua University. Then he obtained his master's degree in physics in the same university, and he now is a current Ph.D. student at the Institute of Photonic Sciences in Spain. His research interests include several topics in quantum information science, such as quantum resource theory, quantum thermodynamics, and the quantum foundation. And let's welcome Chung-Yun.
Thank you so much for the introduction, and also thanks very much for the invitation. It's very nice for me to have this opportunity to introduce my recent result to you. So let me just come to the first page. All right. So today I will just briefly talk about one of our recent results that I have with my supervisor Antonio Asin and my co-supervisor Matteo Taglio. And the title is called Quantum Channel Marginal Problem. Well, and today, rather than giving you a very technical, talking about technical details and proof, I will just focus on a very introductory and from the high-level picture to introduce the key messages of our results. So I hope that, like, for people with different background, you can still more or less follow today's talk. And also, I will try to control my presentation within 30 minutes. So if you have any question, you can just interrupt me and then just ask me. Okay, so let's start. So the title is Quantum Channel Marginal Problem. But then, of course, like, what is marginal problem is still not very clear. And what we really want to study is also like the marginal problem in quantum information. So the very first question that we need to know is like, okay, what is the quantum information that we have in mind, especially for us in this project? What kinds of quantum information and what aspects of quantum information theory that we want to consider in this project? So for me, at least in this project, we want to study the information content of a quantum system and the physics behind it. And this is also the direction in quantum information theory that I always have interest in. And in order to understand this sentence more precisely, maybe it's nice to have a really quick recap of what is information. So let's consider this and suppose that it is a system. If now I just give you this thing without telling you anything more, then basically we know nothing, right? Because there's no information. But if now I divide this system into two parts with equal volume, then we suddenly know something. Because if we call the upper part 1 and the lower part 0, and then if we put some particle inside the system, if the particle is in the upper part, then we know, the system represents 1. And if the particle is in the lower part, then the system represents 0. So by doing something, then we can let the system carry 1 bit of classical information. And if we have these kinds of classical system as the information carrier, then we can have, complicated enough sequence of systems so that we can use them to maybe build a conversations or build a communication. And this is my understanding of classical information. And now we know about what is classical information and how can a system carry classical information. But what can we do with classical information carried by a physical system? So I always love to use the following toy model from thermodynamics to briefly illustrate the power of information and its interdisciplinary application. So now we go back to this case that we have a system that we divided into two parts with equal volumes that I call it V. And now let's consider the following toy model that is like, now from now on everything is ideal and we ignore gravity. That suppose now we put a piston, or say the division, in between the upper and lower part, and we assume no friction. And now we put one single particle of ideal gas in the upper part of this big system. Then what we know is that this ideal gas is located in the upper part. So we know the location. We have the information of the location. And what we can do with this is, if we let the ideal gas expand isothermally, then according to the ideal gas equation, we can compute the work that we can extract, and it's actually kBt long 2. And after the process, after this isothermal expansion, we basically have this situation is that the ideal gas is now in the whole system and we no longer have the information of the location. So by consuming the information of the location, we can extract kBt long 2 amounts of energy, or say kBt long 2 amounts of work. And we can also do the whole process in the opposite way, is that we start with this, that we put the ideal gas in this big system. We have no idea where the ideal gas is in the upper part or the lower part. And then we can compress the system isothermally. And then according to the ideal gas equation, we can compute the energy that we need to consume. We need to pay kBt long 2 amounts of work so that we can compress the system. And after the compression, we know that the ideal gas is located in the upper part. So by consuming energy, we get information of location. So this direction that by consuming information and then we get work is called Caesar engine. And the opposite direction by consuming energy to get deterministic information content, or say to decrease entropy, is called Landauer principle. And this thing just tells us a very important physical message, that is, information is physical, and you can consume information content and then you can get work, and you can also consume energy so that you can get deterministic information content. From here, we learn that information carried by a physical system can be a resource, and this is a very important observation. So we go back to this slide. The directions of quantum information theory that we have interest is that we want to study the information content of a quantum system. So previously, when I used the toy model to introduce what we can do with classical information in thermodynamic sense, it's all about classical system. And how about quantum system? What we can do with the information carried by a quantum system, which is also called quantum information. So we go back to this. This is the classical system that we use for the previous examples. And in this case, we only have two possible deterministic status, which is either 0 or 1. So this is the classical case. But in the quantum world, in a quantum system, we have the so-called superposition. And I guess I just ignored, or say skip the descriptions of the superposition and just told you the consequences that it tells us that there are infinitely many deterministic states of the system that you can consider, rather than just 0 and 1. And this huge difference will actually give us, from the structural point of view, that also a huge difference between classical and the quantum world. By putting quantum physics and the classical bit together, we have the so-called quantum bit, which is actually a two-level quantum system. And then if you have like many quantum bits, or say qubits together, yeah, you can actually do quite a few things that you can never achieve in the classical world. So information carried by a physical system is a resource, and consequently, information carried by a quantum system, or say quantum information, is also a resource in many different senses. And what we have interest is that we put quantum information plus different physical phenomena so we can have different types of resources. And then, interestingly, they can help us to do different things. And it's probably nice to give you a very well-known example that probably most of you or all of you already know, but I think it's still nice to mention here, is that if we have two qubits, then probably the most well-known quantum resource that we have here is the so-called entanglement. Rather than telling you the definitions of entanglement, I'm going to tell you what kinds of things that we can achieve with entanglement, especially something that we can achieve only with entanglement. So consider the following task is that we have a sender and a receiver, and then the sender wants to send an arbitrarily given unknown quantum system, or more precisely, an unknown quantum state to the receiver. And the point is that the state is unknown. And in general, if you only have the classical resources, you can never do it. But you can actually do this if the sender and the receiver share a pair of the so-called maximally entangled state. So suppose that you have two qubits that they are maximally entangled, in the sense that it is the entanglement of in some sense, the highest amounts of entanglement that we can have in a pair of qubits. So what we can do is that once the sender and the receiver pre-share such a highest level of entanglement, then when the sender is given an unknown quantum state, indicated by this bright colored dot, then the sender can apply a joint measurement, the so-called Bell measurement, acting on this dot and half of the pre-share entangled state. And then after the measurement, the sender will consume the entanglement pre-share and then generating some data after the measurement. Then the sender can just send those data through some classical method like making a phone call or some email. Just tell the receiver about the measurement data that the sender just got after the measurement. And then the magic part is that the receiver can just use those data together with some local operations to reconstruct the originally unknown quantum state that is given to the receiver, so to the sender at the very beginning. And this thing can only be achieved if the sender consumes the pre-share entanglement at the very beginning. So by consuming entanglement, in the sense that entanglement is now a resource in this protocol, that the sender and the receiver can achieve something that you can never achieve if you don't have entanglement. So this gives you the flavor of why we treat so many different types of quantum phenomena as resources in the study of quantum information theory, especially in the direction that I have interest. And so this just illustrates one example of quantum resource. There are also many other features of quantum system can also be resources. And one example is the marginal problems that today I want to tell you. So now we can just go to the main topic about the quantum channel marginal problem that we have interest. So quantum channel marginal problem is like abbreviations of quantum mechanical and dynamical marginal problem. But then before telling you the formal definition, maybe it's nice to first tell you what is marginal problem, because I just keep saying this word, keep saying this name, but then without really giving you the definition. So to pretty much like let you or say picture what marginal problem is, maybe let me just borrow an artwork by MC Escher, which is called the water flow. So let's look at this part of this drawing by MC Escher. It looks like part of a building and it looks normal, usual, like there's nothing special. And let's just call this part square and then move to another part of the drawing that I call it triangle. Again, it looks like really normal. It's just like some building structure with some water flowing, but nothing strange. Then we move to the third part that I call a circle, and again, looks very normal. But now, let's just ask the following question. Can these three local parts coexist? And in fact, if we put them together, we observe something strange. Although locally, they look pretty like normal, and then in their overlapping part is also the same. But if we put them together, you can see the water is flowing upward and going down from the water flow and going upward again, which is clearly in violation of some fundamental physical law. So, although those three local configurations, they are locally the same, they cannot coexist because they are violating some physical laws. And in the scientific way, we say those three configurations, they are locally compatible, but actually they are incompatible. So what is marginal problem? Marginal problem is the kinds of problems asking that if you have a big system and then you give me some local configurations, some local behaviors, we want to know whether those local behaviors can coexist at the same time, in the sense that they exist at the same time in the given system. When those local configurations, they are probability distribution, we call them classical marginal problems. And if those local configurations are quantum states, we call them quantum state marginal problem also known as quantum marginal problem in the literature, which has been found applications in, for example, non-locality detection and entanglement theory. So what we want to do is that we first observe that, yes, we already have studies in the classical marginal problem and state marginal problem, but both of them are static. Nothing is moving, right? But in reality, everything is moving. Everything includes time evolution. So we just want to know whether it's possible to upgrade the static marginal problem to the dynamic origin. And this motivates us to replace those configurations by some local quantum dynamics, in the sense that there are some dynamical evolutions of some local quantum systems. And in this sense, those local quantum dynamics is also known as quantum channel. So that's why we give the name quantum channel marginal problem. And we want to know that in a big system, if you observe some local quantum dynamics in the sense of local quantum channels, can they coexist? So this explains the title, quantum channel marginal problem, because it is actually a dynamical generalization of state marginal problem. Normally, we ask the following question. Suppose that we have a big system, and then we are given some local dynamics. We want to know that whether they can coexist. And schematically, let me just use this three body system, or say tripartite system, to illustrate the idea. Suppose that we have a tripartite system, three-body system, and then you have a two-body dynamics in the first and the second system indicated by this box. And then you have another dynamics in the second and the third system, which is represented by this box. Then you want to know whether there exists a global box also representing some dynamics, such that this red box, if you ignore the third system, it will reproduce the dynamics of the first box. If you ignore the first system and then look at the red part, you will actually reproduce the second box. So this would be the question that we have in mind about the marginal problem for quantum dynamics. But before going into the detail, we need to answer two questions at the very beginning, which are, why mass quantum and why mass dynamics? So why these two questions are important? Because we claim that we want to study the marginal problem for quantum dynamics, but then why mass quantum? Is there anything more than classical marginal problem that we can learn? And also why mass dynamics? Because what if the state marginal problem can already tell us everything? So we need to answer these two questions at the very beginning, so that we will understand that the project is like contributing some non-trivial results. In order to do so, let me just show you this tripartite setup in the classical case to answer the first question. So let's consider this tripartite setting with three local systems A, B, C. Suppose that we have the following classical probability distribution, that in B and C we have this square probability distribution PBC. And then in A and B we have another triangle probability distribution PAB. And we further assume that their local behavior in the system B will be the same, in the sense that for the triangle, if you ignore the first system, you will have the probability PB in the system B, which will be the same probability distribution if we ignore the third system in the square probability distribution. Then in this case, we ask the following question. Can we conclude anything about the compatibility of these two local probability distribution? And the answer is yes, because in fact you can construct a global probability distribution such that when you ignore the third one, it reproduces the triangle. When you ignore the first one, it reproduces the square. So in this that we call it ABBC setting, that there's no loop in this triangle setup, that both static and dynamical classical marginal problems are trivial, in the sense that when those local configurations, they are locally the same, then the coexistence is guaranteed. So there's no need to go beyond checking whether they are locally the same or not. But how about quantum case? In the quantum case, for the quantum states, for example, if we put a maximum entangled state in the system BC, and we put another maximum entangled state in the system AB, then these two states, because they are the same state, but share with different systems, so locally they are the same, but can they coexist? And the answer is no, because entanglement is monogamous. So in the simplest AB-BC setup, state marginal problem is already non-trivial, and the thesis behind is entangled monogamy. So why we must consider quantum is because in the quantum case, we get more physics than the classical case. And this pretty much answers the first question that we posed. And now we move to the second question, is that why must consider dynamics rather than static case? So again, the same setting. Now we put this channel here. That is compositions of two channels. First is that in this BC system, you just throw away the system C and then just produce the zero state here. And then you do the swap. Swap means that you exchange the role of system B and C. And then you put the same channel in the system AB. Then when you put these two channels together, in the local system B, they are always the state preparation channel of the case of the zero state. Because first you already prepare in the system, for example, for the triangle, you already prepare in the system A, and then you do the swap. And then also for the square, you prepare in the system C, and then you do the swap. So if we are a local agent in the system B, we always see the output is always a zero state. So those local channels, this triangle channel and the square channel, they are locally the same in the system B. But can they coexist? Again, the answer is no. But the mechanism behind is different, because quantum information cannot be cloned. In the sense that if there exists a tripartite channel that can realize triangle and square at the same time, then you can clone the input in the system B. Because if you look at the triangle channel, for example, if you can input whatever you want in the system B, and then it will be swapped to the output on the system A. And then the same thing will happen by using the square, that you swap it to the output of the system C. So if these two local channels are compatible, if they can coexist, in the sense that there exists a tripartite channel that realizes them at the same time, then you can always clone the input state in the system B by putting them to the system A and system C at the same time, which is in violations of the so-called no-cloning theorem. So why must consider dynamics? Because dynamics give us different physics than the static case. And with these two,
Hello.
First, yes, please.
So I was wondering, what do you mean by two channels at the same time? Because I just couldn't imagine if there's some, if there are two channels, they are compatible, so they can apply at the same time. But there's a one UBB they share, so yeah, I just couldn't imagine that, because I was thinking about maybe if I first apply a channel on AB and later on BC by using it at the same time, then
Okay, so maybe, so by saying compatible, I mean that, for example, if you have this triangle channel and square channel, let me go back to a bit. By saying compatible, I mean that there exists a tripartite channel, like a single channel acting on this tripartite system, such that if you ignore the third system, it will produce the triangle. And if you ignore the first system, it will produce the square. So that's what I mean by saying that they can be realized at the same time, in the sense that it's just a little bit similar to the state case. So if I go back a bit to the state case, when I say two bipartite states, rho AB and rho BC, can coexist, I mean that there exists a tripartite state, sigma ABC, such that if you trace out system C, sigma AB will be the same with rho AB. And if you trace out A, sigma BC will be the same with rho BC. So this is the case for quantum state. And then by saying that two bipartite channels can coexist, I'm doing almost the same thing, that you just replace the state that I mentioned, rho and sigma, you just upgrade them to channel. So I hope that this answers the question.
Yes, thank you.
Yeah, thank you for the question. And so also it's nice to ask this question right now, because from here you can probably again see why it's not moving. Oh yes, you can probably also see why triangle and square that you see here cannot be the result from the single tripartite channel, because if there was a single tripartite channel, say let me call it EABC, such that if you ignore the system C, EAB will be triangle. If you ignore system A, EBC will be square. Then what will happen is that you can put whatever you want in the system B through this tripartite channel EABC. And what will happen is that this whatever input, say, let me just call it rho B, will always be output at the same time to the system A and C. Because if we want to see why it's always output to the system A, you can just observe that EABC, when you ignore system C, will be the same with triangle. So the input rho B will be mapped to the output of the system A. And on the other hand, for the system BC, we say that EBC is the same with the square. So the same input rho B will now be swapped to the output side of the system C. Right? Those are some local behaviors that is guaranteed by triangle and square. So if there was such a tripartite channel EABCs that can realize triangle and square at the same time, then if you look at this tripartite channel globally, we will see that for arbitrary input rho B, it will be mapped to both the output of the system A and the system C at the same time. So you input a rho in the system B, then you output two copies of rho in the system A and system C, which is in violations of the no-collision theorem, because no-collision theorem just tells us that no such a channel can exist. So that's why, but I also understand that, because once we upgrade from the state case to the channel case, it becomes like not very obvious about how to define the partial trace and what do I mean by saying that the marginal of a channel. So actually, this is the part that I didn't really tell you in detail during the presentation. There are actually some details and subtleties about the definitions of the partial trace of channel. It's actually related to the no signaling principle, but I just don't want to make the presentation too complicated. So that's why I didn't mention, but still, thanks for the question. And so maybe we can come back to the presentation. That's what I mean by saying that if these two channels coexist, they will be in violation of some physical law. And then from here, we also learned that why dynamics, because we can actually learn different physics from dynamics rather than in the static case. Okay, now based on these previous observations, we can eventually go back to our central question, which is about the quantum channel marginal problem. We observe this qualitative phenomenon, and then we want to go to the next level by providing a quantitative study. And how to do it is that for the given dynamics, we not only want to know whether they are compatible or not, we also want to know that in the case that when they are incompatible, how incompatible they are. So what we propose is that we define a function that we call it R, such that it is a function of different configurations of different local channels. And you put different local channels inside. If the value is 1, then we say, then those local channels, they are compatible, in the sense that you can find a big single global channel such that when you ignore partial systems, then you will reproduce the given local channel. If the value is strictly less than 1, then they are incompatible. And then the smaller the value is, the more incompatible they are. So what is this function? This is basically the function that we call channel incompatibility robustness. which is defined in this way. So let me briefly explain the definition. You can see that lambda is just like a probability weighting. So it's like it is in the range of 0 and 1. And then lambda is a probability weighting of the given local channel when we mix it with some other channel that we call them nx. And then what we want is that we want to mix the given collection of local channel ex with some other channel nx so that the final mixture will be compatible. From here, we observe that lambda is 1 in the sense that if the maximum lambda value is 1, then it means that the given collection ex, they are already compatible, right? If the maximum lambda is always strictly less than 1, it means that we always need to add some other channel to destroy the incompatibility in the sense that the given collection is incompatible. So that's why it is called robustness. It tells us that how robust the given collection ex, how robust it is when we put some noises to destroy their incompatibility. And those nx is the so-called noise channel that you also the noise in the definitions of robustness. And this will give us a way to see how incompatible the given collection is. Then you may wonder why we want to consider this very specific measure of incompatibility. So one very realistic reason is that because this is a semi-definite program, abbreviated as SDP, which means that you can use MATLAB to compute it in principle. And to see why it is an SDP, I will just quickly go through the detail of this robustness measure. But if you want to see more about the reasoning, you can read our paper. So the robustness definition is given in this gray. It's given in gray on the top, and then in fact you can rewrite it in the following way: that first we have the probability weighting lambda in 0 and 1, and then we can also introduce another variable that we call a rho SS plan, which I just hope that you believe me that this is equivalent to a channel in the system S. And this is actually because this is a choice state of a channel. But what I want to say is that we can use the so-called Choi-Hamelgorski isomorphism to represent a quantum channel in terms of a bipartite quantum state. And why I want to do so is because in the definitions of the robustness, we want the mixture of E with another noise channel N to be compatible. So the strategy is that we want to figure out some way to represent a set of compatible collection. So this rho SS plan will play the role. And first, rho SS plan gives us a global channel, and then we further figure out a necessary and sufficient condition for a global channel to have some marginal channel. And basically, these are just some technical details. So I just quickly go through it. And then the last condition will be just the robustness condition. And what I list all these conditions here is not just, I didn't mean that you will immediately understand what it means. I just want to show you that, look, all of these are linear conditions. So this is an SDP, right? Linear, and all the variables are positive self-definite. This is an SDP. And because this is an SDP, you can compute the gel. Right? And when you compute the gel, you can further show that the strong duality holds. So once you go through all these technical details, and they are all already included in the appendix in the paper, they are like a few pages, so I'm not going to the detail. Once you go through all of this, you can actually use this channel incompatibility robustness to prove that a given collection is incompatible if and only if there exists a collection of Hermitian operators and quantum state such that you have this strict inequality. So how to understand the meaning of this strict inequality is that it is some kinds of witness of channel incompatibility, right? So although I say those operators are Hermitian, but actually they can be further proof that they can be positive operator, and they can be even further rescaled to be part of a POV and part of quantum measurement. So this theorem actually tells us that a given collection of local channel is incompatible if and only if you can always find at least one major and prepared scenario such that you can if we look at the left-hand side of this inequality, this gives you a score in this measure and prepare scenario. And then in this measure and prepare scenario, the score of the given collection, of the given incompatible collections of local channel, will always be strictly higher than the highest possible score that is attainable by compatible local channels. So from here, we call it channel incompatibility witness. And because I already mentioned that it's like a measure and prepare scenario, so it can be naturally cast into a state discrimination task. So in the paper that we also say that, actually a very natural consequence of this theory, of this theorem is that channel incompatibility is necessary and sufficient for advantage in some state discrimination task, and which is a consequence of this strict inequality. And this also justifies the claim that channel incompatibility is a resource, because you can always find out some operational tags such that you can achieve something that you can never achieve if you don't have those resources. Okay, and finally, the take-home messages that I hope to provide is that I hope that at least now we understand why it's a marginal problem, is that in a big physical system, you have some local configurations, you want to know whether they can coexist. And then what we have interest is that we want to study whether when we are given a collections of local quantum dynamics, whether there is a single global one that can realize them simultaneously. And then we have some discussions about why must quantum, because actually quantum case give us more physics, and why must dynamical, because dynamical case give us different physics than the static case. And based on these two observations and discussions, we try to level our qualitative understanding to a quantitative study by providing a robustness measure, and we further use this robustness measure to prove a witness theorem, and then using this witness theorem to provide an operational advantage that if you want to know the detail, you can read our paper. And finally, this is the general information of the paper, and thank you very much for your attention and patience.
Okay, thank you. Yeah. Is there any question from the audience?
Okay, I want to ask some questions. Can you hear my voice?
Yes, yes.
The first question that come to my mind is, are there different quantitative measurement of the you just mentioned that there's a robustness measurement. Is this the first quantitative description, or are there some other quantity to measure the robustness of the violation?
So I guess there are two ways to answer your question. This is a good question, by the way. So my understanding of your question is that are there other quantifiers of a quantum resource? So this is maybe one way to interpret your question. And the answer is yes, there are like many different ways to quantify a quantum resource. And actually, there are also many different robustness to quantify a single quantum resource. And if I go back to the definition here, one simple example is that I hope that you can still see the slide. Can you still see the slide?
Yes.
Okay. So this is actually the so-called generalized robustness, because I don't have any constraint on the channel n. But of course, you can also put some additional constraint on the channel nx by saying that what if now we only allow those nx that are compatible also. And then this is the so-called standard robustness. And then you can also use another robustness measure, is that what if all of these nx are state preparation channel of the white noise? This is again another valid robustness, and they will always you can just put different constraint on the noise model, and then you can get different robustness measure.
Okay.
Yes, and then please
go ahead. Sorry, I just
okay.
organizing my understanding. So you say that when you restrict the n of x into some classes, so it comes out different measurements of this R of epsilon.
Yeah, it will give you different kinds of robustness. And then apart from robustness, you can also use other ways to quantify a quantum resource. So let's just treat channel incompatibility as one specific quantum resource. So in the resource theory, you can just basically use different kinds of distance measure to quantify basically a broad class of quantum resource. And then, yeah, this basically, it takes hours to tell you like all the possible quantifiers. So that's why I say it's a good question. So I would say that, yeah, there are like many other different ways to quantify different quantum resources, but because channel incompatibility in the sense that we define is we are probably the first paper mentioning these kinds of definitions. So I would say that currently the channel incompatibility robustness is probably the only major that in the literature for the channel incompatibility robustness. So this is actually the second answer to your question.
Okay, so for this special task, it's probably the first quantitative way to describe the robust incompatibility robustness. For this issue, it probably is the first one to quantitate.
Yeah, I would say probably.
Okay, thanks.
Yes.
I have a question before on the first part of this lecture. So
Sure.
You have two directions to extend these problems from the very first, the classical and static. I'm thinking, what is the analog of the classical and dynamical problem? Are there how to because my understanding in your contents, the dynamical versus static is to replace the quantum state into the quantum channel. So what is the classical and dynamical problem for this special?
Okay, good question.
Okay.
Yeah. So I would probably say, so that maybe wait me for a second. I think probably it's easier if I share my paper. Let me share my paper. Let me share my paper. Can you see the PDF?
Yes. My camera has some issues, so
Okay.
can I open it? Fine. Okay.
But now I guess you can see the PDF that I'm
yes,
sharing.
the PDF is clear. Yes.
Okay, so in the classical case, just very roughly speaking, is that you can also define the so-called dynamics. Is that it's like a stochastic matrix. If you look at equation 3, it's just that you have some probability input, and then you have some big matrix that map this input probability distribution to some output probability distribution. So I would say this is a classical analog of dynamics. And then, of course, we know that we can always represent classical probability distribution in a quantum system, right? You just consider incoherent states. Then it's basically classical probability distribution. You fix a quantum basis, and then you just consider the diagonal states, the state that diagonal in this basis. So this will be somehow like the classical versions of the quantum state. That's also sometimes people say incoherent states are classical. So you can actually use pretty much the same way to use a quantum channel to represent the so-called classical channel. Is that it's just like some quantum channels that with only input diagonal state and also output diagonal states. So I hope that is roughly explain or say answer your question. Basically, it's just like some matrix with input probability distribution, also output probability distribution. Yes.
Okay, thanks. So it's about the Markov matrix issues. So you have two marginal Markov matrix. Can you combine them together? The whole three-party Markov matrix is something like that.
Could be. I would say could be.
So for some technical issue, I want to ask more questions. So for the quantum channel part, the technical you use is to transform the channel into the choice state. So the definition involves only the choice representation or are there other representation works? For example, cross or something vectorization are that kind of representation of quantum channel also can be used to describe this problem?
Okay. So yeah, so that's a good question, because indeed we have different kinds of representations of a quantum channel. But then in order to write the robustness as an SDP, we need some linear conditions. So it turns out that usually using the choice state will be the best, at least to my knowledge, especially if you look at the equation A, is the definition of the choice state. So it's quite linear in the sense that we want. And then another good thing is the equation 9. Equation 9 is actually a condition for a big channel to have a well-defined marginal channel. Right? There are some technical terms that I use here, but basically equation 9 is something that we really need to put inside our SDP. And then equation 9 is actually a condition that's given by choice state. So there are like two reasons why we use choice state in the end. One is that because usually it's kind of like linear. And the second thing is that there are one important condition, which is equation 9, that we need to use choice state. Yeah, okay. So that's a good question. Yeah.
Okay, thanks. So do you think that there's some room to explore other representations of the channel for this problem? Do you think that there's some room to?
Yeah, to be honest, I am not very sure. Yeah, because otherwise you mean like the cloud representation
or something like vectorization representation.
Yeah, I'm actually not very sure.
Okay. Thanks. Yeah. Thanks for your nice talk. Thanks.
Yeah, thank you. Thank you for the questions. Yeah.
I'd just like to comment on that previous question.
Yeah, please.
Yeah, so I mean, of course, I guess if you're willing to do the optimization in a nonlinear way, it should be possible to do it in some other way. Of course, I don't know if there's any advantage if you switch to some vectorized representation of these channels or not. Okay, but let me just say ask something from follow up from previous question. So you mentioned this different robustness if you introduce some constraint on this NX channel.
Yeah.
But my understanding is all of them can be sort of like used to also detect the incompatibility.
Yeah.
But of course, I guess the one without the constraint is maybe in some sense the optimal one. And then if you have a constraint in the noise, then maybe sometimes it detects the incompatibility, but sometimes it doesn't. I don't know if this is the correct way to sort of see this.
Yeah, I guess. Yeah, you can finish first. Sorry.
No. I mean, that was sort of the end of that.
I think you're right, because when you put too much constraints on the noise model, now we can look at equation 11, and this bold-face N is basically the noise that I mentioned. If you put too much constraint, maybe sometimes you cannot detect incompatibility in the sense that the resulting robustness measure is not faithful. Could be. I mean, could it be? Yeah, could be, I guess. Wait. Wait, could it be?
Okay, maybe it's not clear.
Yeah.
Yeah.
But at least one thing for sure is that one thing I do know is that if you replace M by white noise, then definitely the value is like worse than considering all possible channels, because we already compute some examples. Yeah. But an advantage. Yeah, sorry.
No, you can finish because I was going to switch to a different question.
Okay. But actually, I guess one advantage of putting some very specific noise here is that it will be maybe easier for you to extract the global channel, and then easier for you to analyze, what is the complex mixture at the boundary, because sometimes you not only want to know that whether the given collection is compatible or not, you also want to know that which collection help you to achieve the compatibility. and what is the noise model help you to achieve the compatibility. So sometimes you want to know the behavior at the boundary, and then in that sense, if you put some noise model specific in your mind, then it will be easier for you and then quicker for you to extract this information from the MATLAB, I guess.
Okay, yeah. So my question, the one that I wanted to ask is, so based on like this kind of incompatibility robustness that you're doing, okay, I think, okay, so you're doing it for channels, okay, that makes sense. But at least it's not obvious to me that you have to restrict yourself to channels. So if now I'm interested in local operations, and then I can ask, are like two local operations that overlap, do they have like a global quantum operation? So I give up trace preserving property, right? And I feel like you could do it in the similar way, but I don't know if you have considered this or not.
Not yet. Yeah, let me think whether this will cause some. Okay, maybe this is a good question and this is a good idea. But one potential issue is that, so one thing I didn't mention in the talk is that in order to study channel marginal problem, the first thing we need to define is what do I mean by saying that a global channel has a marginal channel, right? Imagine that you have a global channel acting on the bipartite system AB, EAB, and what is its marginal channel in the system A? So how to define the partial trace for a channel? So it turns out to be not very trivial, that it involves some, some kinds of a bit complicated commutative relation with the partial trace, which is equation 4. And then in this sense, why we have equation 4 to help us to define the marginal channel is that we say a global channel, say EAB, has a well-defined marginal channel in the system A if for every global input rho S, for rho AB, that you first ignore the system B and then send this local path through this local evolution, whatever. This should coincide with that first you let this EAB acting on the global input rho AB, and then in the end you ignore the system B. So inside this definition, I mean, there are some complicated things here, but in this definition, one important thing is that trace need to be preserved so that we can be sure that locally the state will be, when you put the partial trace before and after the operation, they will be the same. So I guess this could be one potential issue if we want to extend the channel marginal problem to some operation marginal problem. But still, I think it's a very good idea. Maybe we can do it, and then it should also be relevant because it's more general than channel.
Yeah, I mean, at least I imagine that, at least in some cases, it probably will still work. Yeah, but of course, again, yeah, you're right. I mean, one has to check, like, if everything you have still carries over or not.
Yeah. So I could probably imagine that now, if you want to extend it to the operation, then equation 4 is no longer true, or say no longer the best one for you to define the so-called marginal operation. Yeah, so should probably figure out a new way.
Yeah, that's it. Thanks.
Thank you so much.
I was curious about why the incompatibility robustness is defined as like whether two subchannel can be whether they are incompatibility, and it's not like maybe one big channel can be decomposed to two.
Sorry, could you repeat again the question?
So I was wondering, like, why this incompatibility robustness is defined as like whether a set of channel are they incompatible or not, instead of a big channel whether it can decompose to two sub channel. something like that.
Okay, so maybe I can explain again the definition. Oh, so can you see the equation 11 here?
Yeah.
Okay, so the idea of defining robustness is that, so this bold-face E is the collection that we have in hand. We want to know whether this collection is incompatible or not. Or let's just say in general, this is an object that we have in hand. We want to know whether E has a given quantum resource that we want or not. And one standard way to see whether it is true is that we ask the question. Now we mix this given object, this capital E, with some other object that we just call it N. We mix them together in the sense of some convex mixture. And then we ask to which extent that this mixture will become free, will become useless, will become resourceless. So in this context, yeah, sorry.
But my question maybe is more like, when I add in some noise to the
yes,
this set of channel, so
yes,
I'm making this set of channel less worth, like it becomes but so this incompatibility is defined to between these two channels, instead of like one channel is become a resource. I mean, because if I only have one channel, then this is not, it cannot tell me like whether it is valuable. So it's when I have two channels, so it defines these two channels value to doing something as a resource. I just, maybe it's not clear to me then how, well, you have these two channels, and then I don't know, it's not like if I have entanglement, then it's clear, like it can violate a non-Bell inequality. But I'm not, I feel like if I have two channel and they have, I must have these two. So if I say these two, they have this incompatibility, but if I only have one of them, then what happens? Or I don't know. Yeah.
Okay, so yeah, so it's a good question. So incompatibility is actually a resource shared by at least two channels. And so, which means that this is a quantum phenomenon that you cannot see if you only have one copy of channel. So it's just a little bit like, a little bit like steering or measurement incompatibility, that you need to have multiple objects in order to see this quantum phenomena. And you also mentioned a good point is that at the very beginning, it will be unclear that whether, you have a collection of channels and then you define incompatibility, and why, like in which test or in which operational sense that it can be a resource, right? Because just like entanglement, it can violate Bell inequality, or it can be a resource for teleportation is very clear. But in this sense, what kinds of text is useful? So it turns out that using the main theory that we prove, that you can further construct the text that we call, is listed here, that we call it ensemble state discrimination test, because basically it is an ensemble of state discrimination tests. And then you can define such a test, and you can further show that you can define success probability, and then you can prove the theorem too that we listed here, is that if you have a collection of channels, right? If the collection is incompatible, then if and only if, you can always find out such a text such that this collection give you an advantage. So equation 20, you can just imagine it's just like the flavor is a bit similar to Bell inequality violation. You can just imagine PC just the classical value for the Bell functional, and then E plays the role something like the non-local state that for every non-local state you can find a Bell inequality that can reach the inequality violation. And then we are doing something similar because it's all about convex optimization. And then we can show that now this collection E is incompatible if and only if this strict inequality equation 20 can be achieved. And it's just like in this inequality equation 20, this PDE value actually has a physical interpretation as the success probability in the state definition test that we define. So I hope that this roughly explained that why in the end we can call the channel incompatibility as a resource. It's because, yes, indeed, it provides some advantages in some operational tasks. I hope that is partially answer your question.
Yeah, thanks.
Thank you.
Okay, I mean, I guess you already answered the question, but I just wanted to comment that one of the things that also, like, one of my initial confusions also from this is, okay, so here the problem is really, you know, the local channels and you're asking if they're compatible with a global one, right?
Yeah.
And this is a different question from, given a global channel, does it have well-defined local channels?
Oh, yeah, it's different, yes.
Right, yes, yeah. And okay, I initially I thought like Hsieh was making this kind of confusion. Okay, but it seems like it was something else.
I think that's my confusion. So.
Yeah,
I mean, both are
in
some sense both are interesting questions. They're just not the same question.
Yeah, they are different actually. So actually, whether a global channel has a well-defined marginal channel is equivalent to asking, whether the channel is signaling to this specific local system. So it's all about no signaling. And then we need this in order to define the marginal problem per channel. So these questions need to be answered first so that we can move on to talk about whether a collection of local channel can coexist or not. Yeah, that's pretty much why the paper is structured in this way.
Is there any further question from the audience? If there is no further question, that thanks Chung-Yun again.
Thank you so much.
Thank you for today's nice talk. It's very clear.
Thanks. Yeah, I hope that is clear. I hope that is like